assume that there is something called an adder which is pipelined to a depth of 1, and that I can draw its architecture essentially something like this. So, this is essentially what the unit looks like. It has 2 inputs, 1 output. When I say that it is pipelined to a depth of 1, all that I really am saying over here is the 2 values are added and stored in a register. So, whatever comes out of this hardware module is what was sent in as the inputs to the adder 1 clock cycle earlier. In terms of Verilog, you can think of it very trivially. It's, it would be like one module which says always at pos edge clock out is equal to a plus b. I am going to, in terms of the multiplier, I am going to assume that I have a multiplier which is pipelined to a depth of 2. I will draw it as something looking like this, 2 registers at the output. So, what does this mean? Why would I ever create a multiplier like this where I have a multiplication and then follow it by 2 registers? The point is, most likely that is not how it is implemented internally, right. Internally what might have been done is the multiplier itself is pipelined, meaning that if it was an array multiplier, then after some number of stages of addition of the partial products, I put some registers, layer of registers through it and so on, okay. But as far as the outside world is concerned, I do not care how the internal implementation of the pipeline multiplier is. All that I care about is, after I give an input, a pair of inputs, it takes 2 clock cycles before the corresponding output is generated. But on the very next clock cycle, I can give the next set of inputs and I will get the corresponding outputs 2 cycles later. So, one way of writing this is, for the adder I can say, if this is my timeline and I give in 1, in 2 and I look at out, what I will see is, if this was A0, B0, I will get A0 plus B0 at time 1. Meanwhile, I can give A1, B1 and I will get A1 plus B1 at time 2. I give A2, B2, I will get A2 plus B2 at time 3 and so on. Okay. For the multiplier, if I have once again in 1, in 2 and out, I give A0, B0. When do I get the output? At t equal to 2, not at 1. Okay. So, I get it here. But I can give A1 and B1 here and the output will come here. Okay. I can give A2, B2 here, output will come here at time 4 and so on. Okay. So, in other words, there is a latency equal to 2, initiation interval is equal to 1. Okay. That is essentially the meaning of these statements, pipeline to depth 1 and pipeline to depth 2. Okay. Obviously, the fact that the adder is pipeline to depth 1, multiplier is pipeline to depth 2 are incidental, they are not really relevant to the discussion, but they help to sort of illustrate a point, that is all. So, that is why I have chosen those numbers. With this in place, what we now need to do is, supposing I have 2 edges in my data flow graph, right, like this. Okay. What I am going to say is, I will associate a value, a number with the execution of each node. Okay. Let me call this I and this one j. Okay. I and j must be in the range 0 to n minus 1, where n is the number of clock cycles for one full iteration. So, in the previous examples over here n is equal to 3, in the original one n is equal to 2, the number of cycles that I take to finish one iteration. Okay. So, assume that somehow I have chosen n, okay. And in general, how should I choose n? There is no fixed answer to that. One thing you can very clearly see is there is a minimum value of n that you can easily say, right. If I have some number of additions to be performed and I have only one adder unit, then I need at least that many clock cycles, because at any given clock cycle only one addition can be done, okay. So n must be greater than or equal to the minimum time required for individually operating each of the functions that I want to use in my data flow graph, okay. But beyond that, what should actually be the value of n? Should n be greater than that, or should it be exactly equal to that minimum value? Will I be able to get away with using exactly that minimum value? Can I use a larger value? Those I am not going to answer now, we will look at those later. So all that comes into the topic of what is called scheduling, right, which is where we will go next after this, okay. So how did I decide that these are the time instants at which these operations need to take place, right? More importantly, I mean, this is of course a very trivial example, so it's quite easy to come up with that answer, but for the more complex example, we will see, I'll just give you some numbers magically, right, which will give us a final architecture. How do I come up with those numbers is what we will see later after we have completed. How do I, given those numbers, how do I translate it into an architecture, okay. So if I have an edge in a data flow graph that looks something like this, there is one module A whose output is feeding into B. A is going to execute at time I and B is going to execute at time j, right. Then, and let us say that there are some number of delay elements, some W delay elements on this edge between A to B, right. Initially, let us assume W is equal to 0, right. If W is equal to 0, what can I say about I and j? And let us say in particular that A was an adder. What can I say about I and j? J greater than or equal to I plus 1, okay. So that is essentially, I mean, you remember going back to what we spoke about constraints earlier, I have told you that this is an adder, therefore what I can see over here is j must be greater than or equal to I plus 1, okay. What if it was a multiplier? I do not care what the target is, remember, that is why I am just putting a B over there. Whether the target was a multiplier or an adder, I do not really care. Now in this case, what should it be? J must be greater than or equal to I plus 2, because for the result of that first multiplication to come out, it has a latency of 2 clock cycles. If this was an adder, there was a delay element and this was some other unit, then I actually do not need to worry about j being greater than or equal to I plus 1, right. Now j only needs to be greater than or equal to I plus 1 minus what? Not minus 1, minus n, why n? Because n is the number of clock cycles required to complete one iteration of this data flow graph, which means that the previous sample corresponding to whatever is being produced by the adder and consumed by the module B, right, would have been produced n clock cycles earlier. So as long as j is greater than or equal to I plus 1 minus n, right, I am fine, okay. In fact, I can go one step further and say, if, so by the way, keep in mind this edge that I have drawn over here in the data flow graph corresponds to my original data flow graph, not the one where I have completed resource sharing, not, in other words, it corresponds to this one over here, not to the resource shared version, okay. With that in mind, essentially what I am saying is, if I have such an edge from an adder to some other unit, the adder is scheduled at time I, where I is a number in integer between 0 to n minus 1, and the target unit is scheduled at time j, what will happen is, because the inputs to the adder were given at time I, their outputs will be produced at time I plus 1. So as long as the next unit B is scheduled exactly at time j, I do not need any extra registers to store the output. I can straight away feed the output of the adder, of the pipelined adder, directly to that next unit. Whereas, if there was one sample delay, then what it says is j must be greater than or equal to I plus 1 minus n, because it was n clock cycles earlier that the corresponding sample that I need to use for B was produced. If this is an adder with some n delays on it, and this is I and this is j, now j must be greater than or equal to I plus 1 minus small n times capital N. Okay, or to avoid confusion, I will just use W over here, minus W times N. So, in general, for any data flow graph, for an edge in that data flow graph, if I have decided that the initial actor is going to fire at time I and the destination actor is going to fire at time j, then this condition j is greater than or equal to I plus 1 minus W times N must be satisfied. And I can go one step further and define this term that I am going to call the df between actor A and B is equal to the difference between the actual j and the time when it was actually scheduled. What exactly is the meaning of this will become a little bit more clear when we take up a detailed example and work through it. Okay? We will do that in tomorrow's class because we have run out of time for now. What I want you to think about in the meantime is make sure that you understand exactly the assumptions under which we are working, right. We started off with an example of how a chain of adders could be time shared, right. I could use one hardware adder in order to implement two additions. I could then use that same one hardware adder over 3 clock cycles in order to do two additions, but now I would need extra registers to store the data until the target adder is ready to make use of it. We are extending this idea further, and in order to do that we are making certain assumptions on the kind of hardware that we have. In this particular case, the assumptions that I am going to make are, one is that I have adders that are pipelined to depth 1 and multipliers that are pipelined to depth 2. The meanings of those statements are illustrated by these diagrams. If I have an edge in a data flow graph and I associate certain time instants with when the particular operations can take place, then I need to write certain constraints on those relative time instants. Those constraints are finally what is going to determine A, whether the schedule that I have come up with is valid, and if it is valid, then how does it get implemented, in particular how many registers do I need to add into the hardware design in order to get it working properly.